final. Should get big guy scared right now. Yeah. Okay. So the next topic is areas and distances. So how might you estimate the area under some curvy curve? So what do you know how to find areas of? Circles. But that one you take on faith. Area is pi r squared, which actually nobody in here really has ever been proven. Nobody ever showed you why that's the case. What are the easy things you can find areas of?
Parallelograms.
Yeah, I was going to say, how about all sorts of polygons? Does that make sense? Like anything that has straight sides, you can pretty much divide into triangles and some kind of combination of rectangles, right? That's actually one way that people, when they didn't know the area of a circle was pi r squared, one way they kind of deduced that formula is they took a circle and they inscribed a polygon and circumscribed a polygon. Obviously, a square is a bad choice, but you start to do like a pentagon or a hexagon or an octagon or even like a 7,256-agon, and all of a sudden it looks a lot like a circle. Does that make sense? Yeah. Okay, and that's one way that they deduce that the area of a circle is. You can prove it using that method. Is make inscribe and circumscribe polygons and then limit as the number of sides that polygon goes to infinity. So we're going to use a similar idea, except for we're going to stick to the easiest, nicest shape. Rectangles. So suppose we have some curvy curve, and between A and B we want to find the area underneath that curve. And suppose that, like just to give it some meaning, the y-axis could have units gallons per day, and the x-axis could have units days. What is the area under the curve going to have units of in that case? Yeah. If you do area, the things multiply. If you do area, the things multiply. It's gallons per day. I'm just saying that twice because, it times day gives you gallons. It'll tell you how much, like suppose like that left one is your fuel consumption or something like that, and the right one is times, how many days. You multiply those two things together, you get about how many gallons you've used. Okay, so basic idea, step number 1 is to divide the interval from A to B into subintervals. So chop this thing up into little pieces. Nothing says that those pieces have to be equal size. If your curve behaves differently on, part of the interval, maybe it makes sense to make one big, huge chunk and then smaller chunks elsewhere. For now, we're going to do equal size. And I'm going to call delta x equal b minus a over n, where n is equal to the number of subintervals. Okay. Step 2 is you make boxes.
Do they go over the curve or stay under the curve?
That's a great question. You can do them lots of different ways. So for that method 2A, you can do something that's called use left end points. You can use right end points. You can also do middle points. Oopsies. Oh, now I can't erase my mistake. That's terrible. M-I-D-D. So here's what those would look like. Just color code them. Left endpoints means on that little subinterval, plug in the left point, make a box. And then you can find the area of all those boxes, right? Length times width, length times width, length times width, length times width, right? And then add them all together. That would be a left endpoint. A right endpoint means on each subinterval, plug in the right point. So that's going to give us boxes that look like this. And doesn't appear to be an awesome estimate, but it's great. You could also find this, and then you could find the average of those two, right? that's something called the trapezoid rule. And you'll do more with that in calculus too, but it actually involves taking those 2 points and connecting them with a straight line and making a trapezoid. You could also take middle points, so like take the point in between those and plug that in. And actually this method's kind of cool because notice how it kind of, like especially in that last box, it kind of both overestimates and then underestimates at the same time, and those things kind of cancel each other out a little bit. This midpoint estimate is actually really accurate. And it doesn't take making very many pieces to make it a really good estimate. And of course, if your estimate wasn't good enough, how could you make it better? You have more subintervals, right? And if you have a computer, that's really easy, isn't it? You just like tell it, okay, I want you could program this in. You can say, okay, I want 100 subintervals or 1,000 or 1,000,000. And all of a sudden, like, once those answers become indistinguishable from each other from one iteration to the next, maybe you're like, okay, that's good enough. And there are also formal estimation formulas to tell you how many subintervals you have to get a certain accuracy. And that depends on the curve itself, because if the curve is like steeper, it's going to be different versus if it's flatter. Yeah. That estimation thing we did last time, we've done some estimation things, and they do different things. So the estimation things we've done in the past, like estimate the value of a function at a point, or the differentials estimate like how fast something is changing, or we did that Newton's method estimates the zeros of a function. So the estimation techniques, they're similar in the fact that they're all estimation techniques, but this one estimates area. The other ones we did don't estimate area. Okay. So let's do this with a specific curve. So suppose we take the curve y equals x squared, and we have it from 0 to 1. So the point curve goes through 0, 0, and the point 1, 1. It's a parabola. I want to estimate the area under this curve using left endpoints, and I failed to specify this, but we should say n equals 4, as in 4 subintervals. And unless you're told otherwise, your subintervals should just have equal width. There is a homework problem. It's about the Space Shuttle Endeavour, and the subintervals are not all the same width, okay? Just FYI, that does exist. It's one of those homework problems, but it's totally obvious. Okay, so if we're going to divide the interval from 0 to 1 into 4 pieces, how wide should each piece be? It'll be, you said, a quarter. Yep, you can find that by doing 1 minus 0 over 4, or a quarter. Okay, so our first, we have a quarter, a half, 3/4. Okay, so left endpoint means on every single subinterval, so we've got the subinterval from 0 to a quarter to a half to 3/4, and 3/4 to 1. Take the left endpoint of the subinterval and plug it into the function. So from 0 to a quarter, what's the left endpoint? It's just 0. And when you plug in 0, you get 0. So that box is a no box. It has no height. The next box, you plug in a quarter. It looks like this. Then you plug in 1/2, and then you plug in 3/4. And I'm pretty sure if your function is increasing, the left endpoints will always be an underestimate. You can think, you can increase concave up or increase concave down, and in both cases, it is the case that it's an underestimate. So this is called L4, L for left, and then the subscript 4 tells you how many pieces you did. And then just add up the areas of the boxes. I'm going to do it like kind of a long way the first time, and there will be a slight shortcut we can use for the next one. So what's the height of the first box? And what's its width? Officially, its width is 1/4, right? How would you find the height of the next box? How would you figure out how tall this box is? Plug it in to be specific about plug. What do you mean by it?
Into the
1/4 into.
y is equal to x squared.
Exactly. So 1/4 squared, and then times another 1/4 that is the width. Because you find the y is the height, right? You plug that left number into x squared. How do you find the height of box number 3? 1/2 squared. And then also times 1/4, right? And how about the height of the last box? What do you plug in? 3/4, yep. Squared times 1/4. Is it clear to everybody that every single, as long as your intervals are of equal width, every single term will have a 1/4 factor? So to save myself like lots of writing, I'm going to take that 1/4 out and say 0 plus 1/4 squared plus 1/2 squared plus. I mean, I might just skip to that step right away because every single thing will always have that width 1/4. So that's 1/4 times what? What's 1/4 squared? 1/16. And then 1/4, and then, and getting a common denominator inside the parentheses, that 1/4 is the same as 4/16. So I think that gives us 14/16. Do you guys agree with that? And then you can cross-reduce that 14 and that 4, which will give you 7/32. And obviously, doing this by hand is definitely not the best method, right? I mean, like, if you want to do this well, you could make a computer program that does it quickly, right? If you feel like doing that in your spare time, once this class is over, you can do that.
Can I just do it now and use it on my test?
You can do it now and use it on your homework. Okay, so let's do the same thing but with right endpoints. So same idea, same picture. 0 to 1. The width of my intervals does not change, but the number that you plug in does. So first I plug in 1/4, then I plug in 1/2, then I plug in 3/4, and finally I plug in, pretend that that's right there, plug in 1. And for this, you use R for right, sub 4, meaning 4 subintervals. I'm going to factor my width out because every single thing has a width of 1/4. What's the height of the first box? 1/4 squared, so 1/16. Is that okay? What's the height of the second box? 1/2 squared, 1/4, right? The next box's height is, and the last box's height is 1 squared. So that'll be 1/4, 1/16, 1/4, 9/16, and 1. Common denominator, right? 4/4 and 16/16. 14. Does 30/16 seem correct? I think that's right. Because you've got a 16th, 4/16, 9/16. That's 14, right? Plus 16 does make 30. So that reduces to, I think, 15/32. Well, I was multiplying by 4/4. I mean, that's what you do to get a common denominator, so it really is 4/16. The same thing, this is 16/16. Okay, great.
Do people forget, I don't know, the quarter?
Oh, it can happen, definitely. And there's oftentimes to make the arithmetic easier, it can make the width equal to 1 or something like that. But yeah, people can forget the 1/4. So, yeah, go ahead.
If it was different widths, then you just plug it in this one and this one.
Yeah, so like if I had divided stuff into, say, 8 pieces, then this would have been an eighth, and this would have been 3/8, right? And the numbers you had to plug in 8 different things, right? But it would be an even better estimate.
And you still would be able to take out an eighth.
You'd be able to take out an eighth in that case, yep, because the width of every single box would be 1/8. Just so you know, this is about 0.469, and the previous one, part A, was approximately 0.219.
So when doing these, you should always have a GCF, right?
Say that again?
When doing these, you should always be able to have a GCF, right?
When you're doing these estimation things, there will always be a GCF, yes, because if you're assuming the width is equal, the width will be a GCF, yes, every single time.
So who's closer to the,
Who's closer to the actual thing? Oh, that's a really good question, and I don't think it has a really easy answer.
do we have to just keep going more parts until they,
More parts until they get close together, and we're actually gonna prove that that area is 1/3, and proving it's a bit tricky, okay? So, I think that you can kind of believe that averaging these two gets you a better estimate, right? And does you also believe that if you average those two, you're getting something that's close to 0.3-ish, right? Like 0.4 plus 0.2, 0.3-ish, or actually it's really even. If you add those two together and you find the average, that's we'll say 0.47, and 0.22 is equal to 0.69, and half of that is 0.345, right? Looks like 1/3 seems like a reasonable guess in some sense, doesn't it? So now, did you have a question?
Are you gonna want us to put the answer in?
If I do, I'll ask for it, and WebAssign will do the same, right? If WebAssign doesn't say round to blah places, it wants the exact answer. So don't give it a decimal.
you'll state how many ends we need to do, or how many?
I will state how many ends you need to do. Yep, on this one I just forgot.
Okay.
But I will state how many ends you need to do.
That's
Like,
common.
in the notes, I can tell you that, like, I made a typo, but on the quizzes, I do check better. Yep. And if I forget an end, just let me know, and I'll be like, oh, shoot. Goodness,
So
yes.
the answer
Just
should
do
be
one then.
0.3. Or half of
This is me just guesstimating a better estimate by taking the average of those two.
Okay.
How close would you be to a third if you were down the middle points?
I'd have to do it to know. I don't know for sure. Okay. So we're gonna actually prove that that area is 1/3.
Full sheet of paper there.
It's a full sheet of paper, yep. Okay, but it's partially because you need to draw a good picture of it. Okay. So there's one. Okay. What we're gonna do is we're gonna find an expression for R sub n for any n. This is kind of like a way you could program this right sum into your computer. You could also use left sum, but we're going to get the thing that you could tell your computer to work with. Okay, so step 1 will be that delta x, or the width of your box, will be 1 minus 0 over n, or 1 over n. So this first point is 1 over n. I think to our last example, we had 1/4. The next point was 1/2, which is 2/4, right? And then 3/4, and then 4/4. Does that make sense? So if my first point is 1 over n, what's my next point? And the next point's going to be 3 over n, etc. 1 is the point n over n. Okay, then we had the same thing with a quarter. We had 1/4, 2/4, 3/4, 4/4, right? If we had eighths, it'd be 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, right? Okay. So the right sum, so that's these boxes, all those little boxes there. What is the width of every single box? Almost. The width. 1 over n. And then how do I find the height of the first box? 1 over n squared. What's the height of the next box going to be?
2 over n squared.
Great.
On and on until you get to n over n squared.
On and on until you get to n over n squared. And that's one of those instances where it's actually easier to think about it as n over n instead of 1. Okay, now I'm going to show you something called sigma notation. Have you guys ever seen this big old sum symbol? Maybe you have, maybe you haven't. It's the Greek letter sigma and it, Greek S sum. That's what this stands for. It's a way to write down long sums in a compact fashion. Okay, so first we have 1 over n. So on the top and bottom of the sum, you say where your sum starts and where your sum stops. So look at with this list, I'm going 1, 2, up to n. Does that make sense? So the last thing I add is n. So this top number is n. And then you have a variable where that represents the thing that is changing. Like in the sum, first I have 1 plugged in, then 2, then 3, right? So the way you write that is you say I equals, and I stands for index set. And the number you put that I equals to is what you start with. So it looks like that. And how these things work is they say, take this expression and first plug in 1. So if you take this expression that's written right here and first plug in 1, what do you get? 1 over n times 1 over n, the thing squared, right? And then next you plug in 2, and you get 1 over n times 2 over n squared. And then you plug in 3 up until you plugged in n. Okay, so you get that.
So you want to start at 0 because
If we could begin at, you could begin at 0 if you were doing like the left sum, and then go to n minus 1, but for these it'll be easier. We're always going to do right sums when we do these. And because it doesn't actually, there's a technical thing about areas under curves that if the function, if this limit works out, both the left and right sum are going to equal the same thing. It's just that right sums are a bit easier to work with. Okay. So now I'm going to simplify that just a tad. I equals 1 to n. If I say 1 over n cubed times I squared, does that make sense that that's the same thing? How did I get the over n cubed? What did I do to that I over n that was squared? Squared the top and the bottom, right? And then I multiplied the denominators together. And now think about that big sum as this expression. Does this expression have a greatest common factor? The 1 over n, and also the n's in all the n's in the denominator, because every single denominator has n squared, doesn't it? So what that says is that this 1 over n cubed can factor out of that sigma thing. Okay. So now this is the point at which there is a trick that you don't have to memorize, but you might have to use in your homework. There is a formula that adds this up. So like what that thing is doing is doing 1 plus 2 squared plus 3 squared up to n squared. And the formula that adds that up is, I don't have to memorize either, n plus 1, 2n plus 1 over 6. I don't know who came up with it or how they were so genius. The way you prove that it's correct is use something called induction, which you guys don't know yet. But that's a logical jump you don't have to make on your own. But that's something that can be shown. So using this formula, you could find the right estimate if your n was 100 by plugging in n equals 100. You could find your estimate by plugging in 1,000 or 1,000,000, okay? Does that idea make sense? Other than this jump, I know the jump from there to there should make you feel weird, okay? Like, that's okay. How would you find the sum exactly?
You multiply it out?
That will find you the right estimate exactly. So n squared plus n, 2n plus 1 over 6n cubed. Or multiplying it out some more, you get 2n cubed plus 3n squared plus n over 6n cubed. As long as you plug in a specific n, this will always be an estimate. So the exact answer is found if you take the limit as n goes to infinity of this thing. That's how you get it exactly. You could use L'Hopital's rule, or you could just use rules you know about horizontal asymptotes.
And can you factor in n?
Oh yeah, you could also cancel an n, right?
Yeah.
But even easier, because the degree of the numerator and denominator are both 3, isn't this just going to be 2/6 or a third? We did a lot of limits like that in section, God, was it 2/6, I think? It was infinite limits. And as long as the powers of the numerator and denominator are the same, the limit was the ratio of their coefficients, right? So that's how you actually prove the limit is the sum is 1/3. I'm not going to make you do any of that, okay? But I just have to show you where it comes from. We'll do a little bit more of that tomorrow as well, because there's so many details. But I think if you make this jump from the box thing to the thing up to the arrow, it's not super awful, right? Find an expression, do some algebra, make a summation thing. Okay. So that's left sums, right sums. I think we took, is that all right-ish? Okay. So if, with our parabola, a parabola is an increasing function, right? When we did left sums, they were underestimates, right? When we do right sums, they were overestimates, yes? Okay. So those are called lower and upper sums, but if your function does some increasing and then some decreasing, does it make sense that eventually, after some point in time, it's not as if a left sum is always going to be an overestimate or a right sum is going to be an underestimate. If you have the function changing behavior, like increase, decrease in the middle, it's not clear what kind of estimate you have if it's over or under. So we're going to find lower and upper sums by specifically picking points so that for an upper sum, we have an overestimate, and for a lower sum, we have an underestimate, which won't mean always picking left points or right points. And there should be pretty easy pictures for you to actually draw on your own. Okay, so like I hope you can really draw 2 plus x squared.
Yeah.
Yes, at most.
It's x squared 2 units up. Right?
Exactly, it's x squared 2 units up. So 1, 2 goes through that point. When we input 1, we get 3, right? And when you input -2 and 2, you get, I believe, 6. Does that seem right? If you can't graph that, I'm going to be mean. Go back to calculus. Okay.
I really despise graphing things without graphing paper.
This is why I give you grids on quizzes. So n equals 4. What is the width of each interval?
1.
So delta x will be 2 minus -2 over 4, which is indeed 1. You think if you add -2 to 2 into 4 pieces? Okay. All right. So to make sure that I have overestimates, because I want an upper sum, I've got to plug in -2 there, -1 here, 1 here, and 2 there. So you pick which point, whichever point within that interval means that you have the highest point, the highest y, which may be a left point, may be a right point, or maybe some intermediary point. It might be a point in the middle. So that's called an upper sum. I don't know if there's notation for that. And actually, this thing is symmetric, isn't it? So couldn't you find the area of these two boxes and then multiply by 2? Okay. So 2 times, what's the area of the first box? It's bases. 1 times 3, so its area is 3. What's the area of the next box? 6. So that will be 6 plus 12, or 18. And it isn't always unit squared because x and y may have different units. So if I don't give you units to work with, don't try to give me units. It's okay. So when it asks for an upper sum, it doesn't necessarily mean the left or right sum. That's the only kicker there. Just make sure you draw the picture and make sure your boxes are the overestimates. Let's look at a lower sum. So same picture, same curve.
You just did 2 on each because they're mirrored.
I did 2 on each because they were mirrored. Yep, if you didn't have that mirroring going on, you can't use that symmetry. Yep. Okay. There is 6. Alrighty. So from -2 to -1, to ensure that I have an underestimate, I've got to plug in -1. From -1 to 0, I'd have to plug in 0. 0 to 1, I plug in 1. And 1 to 2, I would plug in 1. So what's the lower sum going to equal? 2 times, what's the area of this box? I think that one's 2. The one that I shaded, at least, is area 2, but maybe you're looking at the other box. The other box has area 3, doesn't it? So what's that? 4 plus 6 is 10. They're pretty far apart because the width of the interval is so wide, right? 1 is kind of a really crappy size, right?
Yeah.
So it's just to make the arithmetic easier so you can show me you get the idea without having to revert to using a calculator. And also, even if you have a calculator, it's pretty tedious to plug in 8 things, right? I mean, like, it can take a long time. So without being able to program your calculator, it's really kind of a pain in the butt. Okay. So the next thing, what I want to do for these is practice making those summation symbols for specific functions. Those summation things, those sigma symbols like we did on the last one. We're not going to actually find the limits. We're just going to write down the summation symbol with a limit in it. Okay? So we have f of x equals root x from 1 to 16. And with these things, step 1 will be to find delta x. So b minus a over n. So right endpoint minus left endpoint divided by how many pieces, which we don't know. So what goes in for b and a?
16.
So that is 15 over n. Our previous one was 1 over n because our width of our interval was 1. So then if this point is 1, what is the next point? How, not 2. If you add on this little bit, you're going to get, this point there is 1 plus 15 over n. Does that make sense? In our previous problem, we had 0, right? And then 0 plus 1 over n was 1 over n. So it's 15 over n past the 1. What's the next point going to be? Not quite. You take this 1 plus 15 over n, and what do you add to it?
15.
You add 15 over n again, which gives you 1 plus 30 over n. That's because the width of the intervals is 15 over n. What's the next one going to be? 1 plus 45 over n. Okay? Notice that 30 is 2 times 15 and 45 is 3 times 15.
Yeah.
Okay,
That's right,
yep.
but
Okay, good.
I'm good at
So write sum. So first we plug in that number, then we plug in that number. Okay, so what's the width of every single box?
15 now.
15 over n, yep. Okay, I'm just going to take that GCF out. To find the height of the first box, what do you plug into root x? 1 plus 15 over n. For the next, what do you plug into the root function?
1 plus 30.
And then next, we plug in 1 plus 45 over n. Up to the last thing you plug in is going to be 1 plus 15n over n. And you can check and see that this thing should be your last endpoint. Okay, so that's 15 over n, sum sign, I equals 1 to n. That part's always going to be the same. They're not squared because we're not plugging into the squared function. We're plugging it into the root function. Yeah.
Wait, which part was always missing?
The I equals 1 to n. Because you're doing a right sum. Okay, something in this expression, in every single term of the sum, something is not, there are a couple things that are not changing. What are they? Yeah.
Not pertaining to this, but just, so the larger picture is like the point of all these is to learn how to sum up all those intervals, because technically you could just keep going, right?
Yeah, yeah.
Yeah, okay.
It's a point is to get like a formula you could use in general for like any n
I'm like,
that you could then
see,
plug
like,
in.
We only go 4 spaces and then we're like at the end and we hit.
Yeah, oh yeah, yeah. Well, the point is they keep, yeah, that's what this, oh, good question. This dot, dot, dot in the middle means the pattern keeps going. Yeah, it goes forever and you're like, okay, I get the gist of the pattern. That's what that dot, dot, dot symbolizes. Now, is it clear that every single thing has a 1 in it? Okay, and now which part of this is changing? The numerators. The first one is 15. The second one is 30, which is 2 times 15, right? The next one is 45, which is, and next you're going to have 60, which is 4 times 15. So how you put that in the expression is you say 15I over n. And then you think, when you plug in 1, do you get that first term? When you plug in 2, do you get the second term? When you plug in 3, do you get the third, etc.? That's how I is the thing that's going up or down or indexing or changing. And once you have that, the exact, I don't know why I just wrote exact. The exact thing, like with a limit, is limit n goes to infinity of my thing in the box. That's all. So once you get the right expression, the answer is just, it's the limit of that expression is the exact area. Yes?
And so at the bottom, the I equals 1, that just says where it started.
The I equals 1 says where it started. So sometimes these summation things might begin at I equals 2. And then that means 2 is the first number that you plug in for I. Or they could begin at I equals 70. I mean, it happens.
But they're
In the cases that we're going to deal with, they're always going to begin at 1.
always going up by one.
They're always going up by 1, yep. That index set is always like an integer set. It starts with that number and then counts up by ones.
Could we start at 0?
Yes, you could have. It just is not as easy. So there are these sums. These sums are not unique representations. There are different ways to write them. Okay, let's do one more. So 1 plus x to the 4th from 2, oh, and yeah, well, okay, we'll do this one and we'll go look for patterns. So 1 plus x to the 4th, 2 to 5. Okay, so that's, it looks kind of parabola-ish, but not quite. Shifted up 1 from 2 to 5. So what's the delta x in this case? 3 over n, yep. Do you guys agree with that? It's 5 minus 2 over n. Okay. What's this first number going to be? Our other one was 1 plus 15 over n, right? What's this one going to be? 2 plus 3 over n. Right? Because you go 3 over n past 2, right? What's the next one going to be? 2 plus 6 over n. Okay. Okay, what's the GCF width of every single box?
3 over
3
n.
over n. Okay, and then we're going to plug the right things as an RIGHT, not correct things, the right endpoints into the function. So we'll have 1 plus 2 plus 3 over n to the 4th. That's plugging in thing 1. Plugging in thing 2 is 1 plus 2 plus 6 over n to the 4th. That's thing 2. Okay.
What's the 1 plus?
The 1 plus came from the fact that that function was 1 plus x to the 4th. Okay.
And that's the area of those particular.
That's the area of this particular box and this particular box. Let's just think about what the last one would be. It'd be 2 plus, I think, 3n over n, which would be what makes 5, right? So plus 1 dot 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 plus 1 plus 2 plus 3n over n to the 4th. Okay, so that's 3 over n. Now when you make it your sum symbol, this 1 never changes. How about the things inside the 4th powers? What other things never change?
2.
The 2 doesn't. And the n, yep. And then how do you think you do this? Numerator, you've got 3 times 1, 3 times 2, 3 times n, right?
3i.
That's going to be 3i. Yep, exactly. Say that again. We start at I equals 1. You think first term, second term, third term. Now there are there are things that are hints inside of this. So look at the thing that we boxed and pretend that you didn't know what the function was originally. And you didn't know what the width of the interval was. How can you tell how wide the interval is from just this limit expression? Which part tells you how wide? Or how long? The 3i over n kind of does, or this 3 does. Do you see what I'm saying? The distance from 2 to 5 is 3, right? Does that make sense? How far it is? Like it's 5 is 3 spaces away from 2, right? How wide was the one in example 4? How wide was the interval in example A? how far from 1 to it was, yeah, and so the width was 15, right? Okay, so the width in this case is 3. How can you find the function? Can you pick it out? We know it's 1 plus x to the 4th, right? So see, you've got the 1 and then stuff to the 4th, right? 1 plus stuff to the 4th. And then can you tell me your start point? Where did my interval start for this thing? 2, right? Do you see that anywhere in here easily? Yeah, it's right there, right? The start point of the previous one was 1, right? And there's a 1 inside that expression. Okay, my main reason to do them this way was because what I want you to do is be able to take this thing and dissect what was the function and what was the interval. And if you can figure out where it starts, how wide, and what the function is, you've got it. Okay. So that's the next question. So first of all, how wide? Width is 2. How about the function? Really simple. The other one we had was 1 plus, I think it was 2 plus 3i over n to the 4th, okay? Was this 2 part of the function in that previous problem? No, the 1 was, right?
2 is the start.
The 2 was the start, nope. The 2 was the start point. So what's the start point for this guy? 5. And what's the function? X to the 10th. Yep. So your function is f of x equals x to the 10th on the interval from 5 to,
2.
starts at 5, width of 2, 5 to 7.
Oh, 2 and 2 to 5.
Yeah, so it's 2 past 5.
I got the I and I've got all scared.
Yeah, so I know it looks all scary, right? But the function is you're doing something to your stuff, right? And the 2 and this part tells you the width. Actually, this 2 does as well, right? They're going to match all the time. So in part B, what's width? How wide is the interval? 5. What's the function? Sine x. And where does the interval start? 2. So f of x equals sine x on the interval from 2 to 7. There actually are other ways to phrase this, but I don't want to confuse you with it. So that's the way I think we should do it. Because there are equivalent things. You can give an equivalent answer, so there might be more than one right one. Okay. I think that really is the hardest thing in this lesson. The next thing, we're back to estimation again. This is just estimation with a picture. So take this picture. I want you to use 6 rectangles to find estimates of each type for the area under the graph from 0 to 12. So first of all, if I'm using 6 pieces and my interval is 12 long, how wide is each piece? 2. Okay, so I go from 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10, and 10 to 12. For left sums, we plug in left points. And I'm pretty sure that WebAssign does have some tolerance for when you estimate that if you're within a certain margin of error, it still gives you full credit because it recognizes you do have to actually guess a little bit. So what's the height of the first box? Appears to be 9. The next box I said was 8.8. Does that seem like a reasonable guess? Okay, this next box right there, I said 8.2. That next box, I said 7.3 because I wanted to do something with an odd decimal. And that one I think is pretty much exactly 6. And this last one is pretty much exactly 4. And so you can all calculate if you have to. I got 86.6. You know, it's about, because those were definitely guesstimations.
Nice to get rid of your cursor over, get a good spot.
Yeah, I'm gonna do R6 right here as well, just so I can keep in mind my estimates. So the width is still 2.
What is it, double I?
Say that again?
Double I?
Oh, I think that's on your paper as double I. Yeah. So the right boxes will look like this. They are going to be underestimates, aren't they? Okay, so there we go. Right, 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 right. So the first number we'd use would be 8.8. You see how I'm going to reuse all those points? Okay, so 8.8, 8.2, 7.3, 6, 4. Does that make sense? Because plugging in the right endpoint for the first box is the same as plugging in the left endpoint for the second box. What's the only box we have to also add on the area of? The little one. Is that what somebody said? The little one? So what is the height of that box appear to be? 1. And that came out to be 72.6.
Pretty close.
They're pretty close together. I mean, they're not that bad.
I mean, compared to the other ones.
Yeah, compared to the other one we saw where they were like pretty far apart. Okay, so part B is, M6, so midpoints. So 2, 4, 6, 8, 10. So what is the middle number in between 0 and 2? 1. So that means you take your height by plugging in 1. Between 2 and 4, you plug in 3, right? Between 4 and 5, 4 and 6, you plug in 5. Plug in 7. Plug in 9. And then plug in 11. And at least from the picture, do you agree that this thing seems to do a better job compared to any of the other methods? Okay. So I guesstimated 2, 8.9, 8.5, 8.7. I said 7.8, 6.8, 5, and 2.8. Notice there are 1, 2, 3, 4, 5, 6. Oh shoot, there are 7. There shouldn't be 7. Did I double something up? The 8.7 shouldn't be there. Cross it off. I took it from the problem above. Transposed 7.8, made 8.7. And that gave me, there should be 6 of them. Yep. Because you have 6 boxes, you should have 6 heights. The delta x didn't change, did it? The width is still 2. Mm-hmm.
So now just take the average.
It actually doesn't. So it's a good question, but it's not. The midpoint rule does not actually take the average of the left and right sums. If you average the left and right sum, what that's equivalent to is actually taking these 2 endpoints and connecting them with a straight line. And they actually end up being different estimates. It turns out the midpoint estimate, where you actually plug in middle numbers, is more accurate than averaging the left and the right estimates. And you can convince yourself that they're not equal by just taking part I and part double I and adding them and dividing by 2 is not the same thing.
So why don't people just always use that if it's more accurate?
The point is to develop the methods, and sort of it is still a good estimator. It's just, maybe they don't have midpoints. So, okay, So those pictures, was L6 an overestimate or under? L6 was overestimate, R6 was an underestimate. Which gave best estimate? The best was M6. And my explanation is that this one both over and under estimates. Or the errors kind of cancel out a little bit.
You just can't justify your answer.
Yeah. Like there's some reason why you think that's true.
So it's okay if I rob the store as long as I gave the food I stole to the homeless man.
Or something like that. Okay, the last thing I want to do, and I think I'm just going to go like a teensy bit over with this. I'll do example 7, but I'll leave example 8 to you once I tell you one thing. So this is kind of an application of these two things. If you have a curve, so you have oil leaking from a tank at R of T liters per hour, and the rate is decreasing as time passed. So your function R of T goes down. So there's your y-axis, here's your t-axis. It doesn't tell you how it goes down, just that it goes down. Maybe it does that, but it does, the rate goes down. So if you know your function is decreasing, the left sum is an overestimate because the function is decreasing. What about the right sum? What did you say? I couldn't hear you. Underestimate. Okay, so 2, 4, 6, 8, 10. And then, okay, so now think about, let's find L6. Wait, why do I say 6? L5, sorry, this is L5. So if you find your left sum, or for any sum, what is the width of every single box? 2. How would you find the height of the first box? What would you plug in? You'd input 0, right? And what comes out is? Next, you're going to input 2, and what comes out?
7.6.
And then 6.8. So that's box 1, box 2, box 3. What do you input next? And then last, you input, and you don't use that last point. Does that make sense? I think 5 boxes, right? Okay, and this ends up giving you 70. What are its units? Liters. And that's your overestimate. What's going to change for the right sum? What are you not going to use this time? The first one. And you will use the last one. So 2 times 7.6 plus 6.8 plus 6.2 plus 5.7 plus 5.3. I did. Thanks. That gives you 63.2 liters. Is that all right? Okay. Example 8 is pretty much the same thing, except for one small tricky technicality. And if you're ahead, look at it and see if you can figure out what the small tricky technicality might be. Say that again? Yeah, second, think about what might make more sense. You're talking about a car being driven for 30 seconds. You can either change seconds into hours, or you can change miles into feet. Does that make sense? And I think what WebAssign will tell you what the units will be, because they'll probably put, it puts units usually there, so you've got to be in the right units. I would change miles per hour into feet per second. The conversion factor for that is 5,280 feet per 3,600 seconds. But just watch out for stuff like that on your homework. And typically, short time interval, probably also want to do a small unit of measure. Because, I mean, you're not going to go very many miles in 30 seconds, but it would be more sense to talk about it in terms of feet. So, that's all I need to say about that one, I think. Because if you can do the conversion, it's the exact same things for left sums and right sums, right? Just watch out for stuff like that.